Log on, tune in, find out. Another good idea from Cambridge.
I don't know who Vengazhiyil is in the publication. He had written a lot of paper under V.R. Joseph. You see the Joseph in Technometric and other journal. This is the Joseph. So I want to warn you. When you write grant proposal, you always write a footnote about it. Otherwise, he will not get good scores. Okay. So his title is Engineering-Driven Statistical Adjustment and Calibration.
Good afternoon. First, I would like to thank Steve Gilmore for the invitation. It's an honor to present here. My topic is on statistical adjustment and calibration. It's a topic that I have been working for like 3-4 years, but the one I'm going to talk here, engineering-driven calibration, is something new. Only a few months back, I started doing this, so it's not fully developed. But when Steve told me that the session is on industry and technology, I still thought this would fit in well and could get feedback from you. Okay, so two types of models that we are considering: the statistical models, the usual regression models. The predictions are very good when we try to predict closer to the data, but they can be poor when we try to predict away from the data. Whereas the engineering models, what I mean by engineering models are the models that are developed based on the physics of the process, okay, like analytical models and finite element models. They have some physical meaning in their predictions, but often not accurate because several assumptions are made in deriving those physics-based models. So there are advantages and disadvantages in each type of approach. So the problem I am trying to solve is, can we integrate them to do better predictions? So here is an example on micro turning, and the engineer wants to predict the surface roughness after that machining operation with respect to the feed rate of the tool. So the engineers have their approach, like using the geometry and kinematics of the process. They can derive a relationship between this distance and the feed rate, as well as the nose radius, and it's a very simple relationship like this, a quadratic relationship. So the surface roughness will increase with respect to feed rate in this quadratic fashion. But then they did real experiments and got data is here. So, and why is it happening? Again, several assumptions are made in deriving that simple formula. You know, you approximate a curve by a straight line, and many other things are neglected. The plasticity, everything is neglected. So, in a micro turning, you know, that becomes more crucial, and you start seeing the differences. So what's the solution here? So one possibility is ignore the engineering model and fit a statistical model, like a quadratic model. It fits the data very well, and we can do good predictions in this region, but we are not sure outside that region. So the objective is now to create something like this. It takes into account of the engineering model, but also fits the data well. So it combines these two and hopefully give better predictions. And in this particular case, you can see this for illustration, because I took the data out, you know, but fitted the models only using this portion of the data, but it fits well, and that gives the message that there are good things in both, and if we combine them, we can do better. So that's the topic of model calibration. It's a very old topic. So like the engineering model may have some unknown parameters, and when we have some, so those are called the calibration parameters. And when we have some data, we can estimate them, plug it in. So that combines the engineering model with the data, and so it will be better. But the problem with this approach is the physical model itself may not be very accurate. There may be something wrong with the physical model because of the assumptions. So, if you just estimate the eta and plug it in, that predictions may not work well in all cases. So, a Bayesian methodology was proposed by Kennedy and O'Hagan. So, in this pictorial, it can be explained like this. So, let us say this is the engineering model prediction, and we put a prior around the prediction, and we have the data, and we can combine them, get the posterior distribution, and that, say, the mean of that posterior can be treated as the engineering statistical model. So, that is a very simple idea, but the main problem is how to put that prior. If you put the prior in a highly dispersed prior, then you will get a very close to a statistical model, but if it is very a prior very concentrated around that physics based model, then the predictions are also going to be only the physics based model predictions. It won't use the data much. So, putting the prior is a very crucial part of that methodology, and they used a Gaussian process model for doing that. And there is a lot of follow-up work on this, but this also has some problems. Like in this particular approach, they assume the data to be correct. In the previous case, the model is assumed to be correct. Here, the data is assumed to be correct, subject to the random errors, but even that is not true in practice. They can have systematic experimental biases. For example, if I apply that approach, the prediction will be like this using the Gaussian process model. But the engineer may come back and say, oh well, this particular experiment may have some problem, it should not dip like this. When I set the feed, maybe there was something wrong, or that particular part had some other difference. That's why it went down. It doesn't make sense to have a predictive model of this kind, although it fits the data well. The data has some systematic biases because of the experiment. So what's happening here in the GP adjustment, you can see it's a very flexible model. So these are the correlation functions, and there are like n unknown parameters which can be estimated, which can be solved. So it's like an interpolation. So it's like interpolating the mean here. So that's why it fits the data very well, but the prediction can be poor. So, I think I don't need to say more to convince you that when we have more parameters in the model, it fits well, but the prediction can go wrong. So what's the alternative to that? Fit a model with fewer parameters. So here I will describe two approaches. One is a data-driven approach and the engineering-driven approach. So that this is the main topic, but I will show you what's the data-driven approach first. So here is the problem. We have the engineering model and data. So in the GP model, it's a non-parametric model. We can have many basis functions. So in the GP model, so these are the basis functions, n basis functions. So similarly, we can have several basis functions, and then we can do a variable selection and get the final model. So it's like choosing only a few of them. So like a linear regression model, we can have many parameters and choose the one that are really needed. So here is a recent work. So we have used the linear regression models as the basis functions, and so it's a lot of parameters in them, but then do a variable selection. So here we applied the non-negative Garratt procedure and obtain the ones that are really important. So only a few will be finally selected. So it's not a full adjustment, but it will bring the engineering model towards the data with a minimal change. So this is the main topic that I want to give here is the engineering driven approach. Let me get my water. So so only one change I want to make here. So instead of blindly doing a data-driven procedure, have some basis functions and use the data to select, I want to do it with more engineering input. So find out the causes of discrepancy and postulate some models and obtain the engineering statistical model. So it may not be very clear from this picture, but I will show you some case studies. Okay, so that might give you a better idea what I am talking about.
I'm sure we're going to talk about this, but the thing bothered me was the engineer model is monotonic. The statistical model also monotonic, but the final model is not.
Yeah.
Is it?
In that first example, right? Yes. So those are the problems. Yeah. So but monotonicity may not be the only problem. In a high dimensional problem, it's very complex surface, so it may not be even clear whether we are even interpolating or extrapolating. So in a high dimensional problem,
Warriors engineer to become a model with reason, physical, whatever reason.
That's right,
It seems get ignored right here somehow.
that's right. Yeah. So I'm going to present two case studies. One is on friction drilling from this paper. So this is the physical experiment to drill that hole, and they have a finite element experiment that simulate that drilling process. So they have a thermomechanical finite element model for doing that simulation. So here I am looking at one of their output called thrust force. So I'm denoting the small f to denote that finite element model. So x is the tool travel distance and eta is the friction coefficient, which is unknown. It's difficult to measure directly. So the engineers don't know that value and they want to estimate it from data. So here is a plot of that physics-based model for different friction coefficient over the tool travel. So you can see it goes up and then goes to 0. This is the start of the drilling process, 0 force, and once it is drilled, there is no force. The hole is fully penetrated, and the force increases with the decrease in the friction coefficient. Okay, so that's the physics-based model. Okay, now they did the real experiment, and this is the data. That's the black line. So you can see there is a discrepancy. We can try to find the, so what they did is to choose this as their model. Okay, that green one, which is close to that one. We can try to fit a model and try to estimate the best eta, which will give slightly improved one, but not much better. So okay, so here I want to use that second approach, engineering driven approach. How do we solve this problem? Okay, how do we overcome this discrepancy? So the first thing I want to do is to find out why that discrepancy is happening. And in that paper itself they mentioned, oh, this could be because of the deflection of the metal. So when you drill, that gets deflected. So there is more tool travel than actual. So that's why it looks to the left. Okay, so there is a reason they have mentioned, but they didn't do anything because it was difficult to incorporate that in their finite element model. So they did not do anything. But can we do it through a statistical model? We know the reason. Can we incorporate that here? Okay, here is a way to do that. So we know the deflection is proportional to the force. So the actual x is actually x times some constant times the force. So now we can solve the force from that finite element model. So that incorporates that deflection. So that solution, say let's denote it as G, but now I have introduced one new parameter gamma. Okay. So, okay, so now solving that force is not easy because it's a very complex finite element model. So the first step is to approximate it through a statistical model. So here we have fitted a GP model. The log of the force is called a universal kriging model, and the Gaussian process part. So I use this part because usually ordinary kriging is fitted, but in this particular case you can see when x goes to 0, this x goes to 0, this should go to 0, and when x becomes large, then also it should go to 0. If we use just an ordinary kriging model, it may give predictions, going down, negative values. So to avoid that, I put that universal kriging term so that it will go to 0 on both ends. So then we can get that approximate model called the meta model. So f hat. Okay. Now this is very quick to evaluate. So now I can use f hat here and solve for f very quickly. So that's that red curve. So the green is the physics-based model, and after this adjustment, by introducing just one parameter, okay, that becomes that red one fits it better. Okay, it shifted that curve. So based on the engineering understanding, they know that this is the reason, and that we incorporated into this through a statistical model. But still, it's not very good here, right? So there may be some other causes. Okay, so they don't mention that because they didn't proceed further. Okay, they just used that first one. So now I am thinking, okay, the another reason could be maybe it's deflecting more as the drilling progresses. Maybe the hole is becoming smaller and smaller, thickness is reducing, so it will deflect more. So that's my thinking. So okay, then I will introduce one more parameter to explain that. So here I have two parameter models. So gamma 1 for the deflection, gamma 2 for further deflection. So again I can do a nonlinear least square estimation for 3 parameters, and now it becomes this. It fits that area also better. So if I didn't show the graph for the GP model, it almost fits this curve exactly if you apply a GP model, but remember that it has so many parameters in it. Okay, this is just with 1 or 2 parameters, we can do almost as good as that, and has an engineering meaning to it. So that's the approach. Okay. So let me show you one more case study, so maybe you'll get a better idea. So on a laser assisted micro milling process that is being developed at Georgia Tech in the mechanical engineering by these people. So the idea, so they want to cut very hard materials, micro cutting, so the tool breaks. So their idea is to put a laser, soften the material, and then cut it. So this is the setup that they created, XYZ movements for the workpiece and the tool and the laser. So laser will be impinged just before the tool, and the workpiece moves. So again, based on their physics, they can derive the relationships. Okay, like how the forces are acting. So based on that, they can derive the force model. So a lot of geometry, everything is involved in that. But finally, they also need to develop a temperature gradient because it's a laser assisted machining. So they need to know how the temperature is getting distributed and how that softening the material. So they can put all those things together into a physics based model. So this is their physics based model. There's no statistics in it. It's a very complex model. And final predictions. So here is the red is the prediction. Okay. This curve is the actual. So actual measured from the experiment. So again, they are not matching very well, the actual and the predicted. So again, there are different approaches to solve this problem, like fitting GP model or a data-driven approach. But here again, I am trying to use an engineering-driven approach on trying to understand what causes this discrepancy. And discussing with them, they suggested that it could be due to a spindle runout. You know, the spindle is not it's rotating like this. There is a runout for that. It's not stable. So that's what. It's not really round, but there is some kind of motion to it. And also there can be a offset. The center may be slightly shifted. So these things are not incorporated in their physics-based model. So this is happening in their machine. So one way to incorporate that is through a statistical model. So we put this is a rotating motion. So these are the three regression parameters, A, B, and C. C captures that offset. And now we can incorporate that into their model. Okay, so that comes in there, and then calibrate it. You know, estimate those parameters. So again, here calibration is not very easy because the physics-based model is very complex. It takes about half an hour to evaluate this part, just one evaluation. So what we did is to approximate this part of the model using a meta model. So again, we had to do a computer experiment fit Kriging model for that particular part of the whole model. And then the other equations are very easy to evaluate. So that part can be quickly evaluated. So only the temperature calculations are time consuming. So that was approximated using the meta model. And now we can proceed for the calibration. So this is our statistical model. There are 5 unknown parameters. So there is one more parameter that we had to introduce because the measurements are continuous. And this also the physics-based model like this. So where to start is not very clear. So we have to align it properly. At what angle the tool cuts the material is not known. So that's that A, just to align the physics-based model and the actual data. So there are 5 unknown parameters which can be estimated, nonlinear least squares. But we did a little bit more than that because A, B, and C actually becomes linear. So we can get the least squares expression for that, and then solve only beta and A through a nonlinear optimization. So that's the calibrated model. You can see it fits the data better. Okay, it's not again fully explaining, but according to the engineers, this will serve their purpose, okay, to optimize the process. So in conclusions, I have shown you 2 approaches for adjustment and calibration. The first is the data-driven. The advantage of data-driven approach is it's very general. Any problem you see, you can do that. You know, have some basis functions and select, or even the GP model adjustment. But it lacks the physical understanding. Whereas the engineering-driven approach, if you just give me the data, I cannot do anything. You know. I need to identify the reason. So it's a problem-specific approach. Identify the causes and postulate models to address that, and then calibrate. So it has better physical interpretation. So there's still more work to be done on how to identify the causes and postulate models, but so it's a work in progress. So still I wanted to show you this. Thank you.
Question, comment?
So this may be quite a long question, but in the first edition of Box and Draper's book on response surfaces, there's an interesting chapter on links between empirical and mechanistic models.
Yes.
where they basically express a second order polynomial in canonical form
Yes.
and then simplify it and use that to motivate some possible engineering or mechanistic model.
Yeah.
I wondered, with things like Gaussian process models, would there be any scope for reparameterizing or somehow re-expressing them, which would help to motivate some of the possible engineering driven models?
Yeah, that's a very good question. I don't know, because GP model is so flexible. You know, in what way, whether you can impose such as the monotonicity restriction, you know, those kind of things are not very clear yet. You know, I haven't seen any work of that kind. But it's a good topic.
Other question?
In your, well, I don't know, first example of two last examples,
Yes.
look to me as if you might be able just to transform the x a bit, actually.
Transform the x a bit.
Yes. To some extent, is that more relevant?
Yeah. In this
That
particular.
example, the previous,
Yes.
yes, that's the thing, isn't it?
Yeah. So transform the x.
That's, if you go, that's after you've done a bit of fiddling, isn't it?
Yeah.
If you go a bit earlier,
Yeah, that's true. We can try to just purely based on some statistical thinking, we can try to transform x and try to fit the data. But I want to go with that engineering-driven intuition, you know, so that they will accept what we are proposing. You know, they understand better.
but I mean, x,
Yes.
x is a distance or something, isn't
Yes,
it?
yes,
So
yes.
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 If it's bending a bit, then perhaps it does need some,
Yes.
isn't quite what they
Yes. For example, like this is also like a transformation on the x. You know?
Yes.
Yeah, but something that they will like.
Yes.
Yeah.
Thank you.
Other question? Then I have one. You mentioned that your alternative to Kriging, and Kriging of course an interpolator with a lot of parameters,
Yes.
and the prediction may not be good. Did you run any study or any simulation analytical to show when actually run prediction,
Yeah.
your hybrid approach is much better than Kriging?
Yes. So we have done several simulations. Here's a list of papers. So this particular paper is on that data-driven approach. So there we do a lot of simulations comparing a data-driven approach and just a GP model fit. And in many cases, you know, a simplified adjustment predicts better.
Okay, I think we now should move on to the tea break.